begin with the review of lecture 34, but today we'll be studying some very interesting new topics. First of all, I would like to introduce two terms or two concepts which are very important, very useful for us in our understanding of diversity. One of them is called array gain, the other one is called diversity gain. It seems like we're using the same names over and over again, but there is some interesting and important differences that help us in our understanding of the whole concept of diversity. Moving from received diversity, we will now talk about transmit diversity. Alamouti code is a very famous discovery in 1998, which showed us that you can achieve the benefits of diversity without multiple antennas at the receiver. And then we will move from that to the next unit of study. And the next unit of study is on understanding the capacity of a channel. This is very closely linked to Shannon's capacity of a AWGN channel. However, we are now talking about a wireless channel, and that's our goal, is to study the capacity of a wireless channel, Shannon capacity as applied to a wireless channel. Okay, so there are several interesting variations from what you would have already studied in digital communications. But first, let's look at a quick summary of the points that we have covered so far. And in any concept, it's always good for us to sort of have a big picture. So the big picture of diversity looks like this. So the concept of diversity, the benefits of diversity, or the ways in which we will exploit diversity are twofold. One is transmit diversity, the other one is receive diversity. So far we've been only talking about receive diversity. Today's class we'll talk about transmit diversity. But in receive diversity, we have talked about three different forms. We have talked about the optimal form, which is maximal ratio combining, the simplest form, which is selection combining, and then something in between, which is equal gain combining. And in selection combining, we said there was pre-detection and then there was post-detection. Okay, so several flavors that we have talked about, and we make the note that this is the optimal. This is very close to optimal. So this is something which is quite attractive. We have also used the name co-phasing for equal gain combining. Okay, so keep the names and the relationships all together. This is the selection combining, as you know, is the simplest of the ways of we are doing it. It does give us benefit, but not as much as the ones that are close to optimal. So that is sort of the broad framework. The specific results from yesterday's lecture. The optimal combining method for diversity gives us the diversity SNR as the sum of the individual SNRs, k is equal to 1 through m gamma k. Expected value of gamma MRC is equal to m times gamma. That's a very important result. Then we saw that selection combining, we choose the maximum of the antennas that are SNRs that we have available to us, gamma 1 through gamma m, and we have shown that expected value of gamma selection combining is equal to average SNR of one antenna plus 1 by 2 all the way to 1 by m, since there are m antennas. Okay? And in the last class, we also said that we would like to look at a suboptimal method which did not involve the estimation of the noise variances, because MRC requires us to have the optimal combining coefficients equal to zk star divided by sigma nk whole squared. It requires us to have that quantity, and therefore the estimation of the noise was the challenge. So equal gain combining avoided that. It said that we will use gain terms which did not involve the noise variance. So some constant scale factor does not affect us, zk star divided by mod zk. So basically that's only the phase, and because of the conjugation, it's the negative of the phase of the gain term. This does the co-phasing for us. we showed that the SNR of EGC, through the steps that we showed in the last class, this comes out to be an interesting number, 1 over m summation k equal to 1 through m square root of gamma k whole squared. And specific examples, we can show what this value is. And so the concluding statement about received diversity, we can say as follows. In general, gamma MRC is the best. So we'll say that it's greater than or equal to gamma EGC. In general is strictly greater than, no harm in saying that it's always as good or better than selection combining. This obtains the sum of SNRs, k equal to 1 through m gamma k. This one achieves 1 over m summation k equal to 1 through m square root of gamma k raised whole squared. And the last one is maximum of gamma 1 through gamma m. So m antennas, gamma 1 through gamma m, instantaneous values. Some of them may be at a good value, some of them may be not so good. MRC combines all of them to get the maximum benefit. EGC does something very similar, except it makes the assumption that noise variances are the same. It's not a correct assumption in all scenarios, but it is a good enough, it's an approximation. And of course, selection diversity says I'll only pick the best. I don't worry about the ones that are not so good. So again, each of them have got certain advantages, disadvantages, but at the end of the day, what is the net benefit or average benefit? I will see an average SNR of m gamma here. In this case, I will see something which is close to m gamma, 1 plus m minus 1 into pi by 4, and this one would be gamma into 1 plus 1 by 2 plus 1 over m. Okay? That's a summary statement. So hope you are now confident that once we have the antennas, then we know how the benefits are going to come about. We know how to get the probability of bit errors. So far, we've looked only at the maximal ratio combining, but it does not matter whichever is the method of diversity combining that's given to us. The key thing that we will need is the probability of error as a function of gamma, whichever is the combination scheme that you're using, f gamma of gamma, integral 0 to infinity d gamma. This will be the probability of error in fading. So this depends on the type of diversity that we are going to be using. Okay? Depends on the type of diversity. So for selection diversity, the PDFs can be obtained. And for the equal gain combining, we have not derived it in the class, but the corresponding PDFs are available likewise for MRC as well, depending upon the type of diversity. Okay? So once you're given that, you can then perform the integral, or you can use the moment generating function, and all of these methods are now tools that are available to us. There may be times when you want to do numerical integration, because the integral itself is very difficult to solve. And you may say, I need to get a quick feel for the numbers, so therefore you may do numerical integration. So here is a useful tool for doing numerical integration. So again, this is only meant as to complete the picture and our understanding that yes, integration is good, integration gives us closed form, but you don't necessarily have to do it. You can do numerical integration. Yeah. So here is a method that is quite useful for us. Okay? Now, supposing you are asked to find out the probability of error of BPSK. So probability of error of BPSK is Q function, Q of root 2 gamma. And Q itself is an integral. So Q of Z is a probability that a normalized random variable is greater than Z. that is given by 1 over root 2 pi integral z to infinity e power minus x squared by 2 dx. So basically q itself is a integral, and if I want the performance in fading, it's going to be probability of error of BPSK in fading. I will now have to include the PDF of the fading SNR and compute another integral. So this will be equal to 0 through infinity q of root 2 gamma. Again, this is all familiar stuff, just want to refresh. F gamma of gamma d gamma. Okay. Now actually these are a little bit tricky to interpret because in the context of if I want to do numerical integration, because these are limits that are going towards infinity. So it's always good for us to have finite bounds when we want to do the integration. So here is a way by which we can achieve the finite integration. So here is the first step. Step 1 says that there is an alternate expression for q of z. So alternate expression for q of z. The alternate expression says q of z can also be written in the following fashion. It's an exact expression, 1 over pi integral 0 to pi by 2 e power minus z squared by 2 sine squared phi d phi. Okay. Now we'll take this expression without proof because again the intent is to show that there is a the differences. The first form is an infinite integral, the other one is this is a finite integral, and these are exact expressions. So the advantage is that this is a finite range 0 to pi by 2, 0 comma pi by 2. So again, if you want to implement it in some form of numerical integration like the trapezoidal rule, this would be that. And the range does not depend on z. So that's another important. So the range of integration, the previous one, the range of integration depends on z. Range of integration does not depend on z. That's also another observation, does not depend on z. Z is your argument of the q function. Okay? So therefore, this is a form that is useful for numerical integration. So here is what we would do. We would now see if we can substitute this. So integral 0 through infinity, that's the outer integral. The substitution for q of z, 1 by pi integral 0 to pi by 2 e power minus gamma divided by sine squared phi. Okay. Just needed to make sure, oh, because the root 2 gamma, okay. Sine squared phi d phi, that's the expression for q of z, and then the other terms, let me write that in blue, f gamma of gamma d gamma. Okay. So I've just substituted the expression for the new second alternate expression for q of z. Interchange the limits. What you will find is 1 by pi comes out, it's a constant, integral 0 to pi by 2. The inner integral is 0 through infinity. F gamma of gamma e power minus gamma by sine squared phi d gamma, and then d phi outside. So take a closer look at the integral. What is this? Looks like the moment generating function, right? Except that you have chosen a specific value of, so this is nothing but the moment generating function of gamma, f gamma of s, evaluated at s is equal to minus 1 by sine squared phi. Okay. So the integral now becomes, this becomes equal to the integral 1 by pi integral 0 to pi by 2, the moment generating function phi gamma of minus 1 by sine squared phi minus 1 by sine squared phi d phi. So, if you know the moment generating function of the SNR, then choose values of phi in the range 0 to pi by 2, whatever integrals that you want, spacing that you want, and evaluate the moment generating function at these points at minus 1 by sine squared phi, and basically that becomes your numerical integration step, and it's very straightforward because once phi of gamma is known, so we assume psi gamma of gamma is known. For us, it's known for most of the common PDFs that we encounter, the types of fading that we encounter, and also known for all the different forms of diversity combining. So once this is known, phi is a fixed range from 0 to pi by 2. You can quantize it in whichever a number of steps you want, and then implement the numerical integration. Okay, so this is a good way for us to implement. So just as one last observation, phi gamma MRC of S. What is that? What is the moment generating function of maximal ratio combining? We derived it in the last class. It is 1 over 1 minus S gamma raised to the power m. Okay? So if somebody were to ask you probability of error of BPSK in the presence of maximal ratio combining, of course, you can do some very elegant integration. We will show how that can be done. But you can also do simple numerical integration of the form 1 by pi integral 0 to pi by 2 1 over 1 plus gamma by sine squared phi the whole raised to the power m d phi. Right. Few lines MATLAB program, and you will get the performance of the bit error rate in maximal ratio combining. Okay. So again, it's good for you to have all the tools available so that you can quickly estimate what the bit error rate is, what the performance is, and for those of you who would like to study this in more detail, please look at Goldsmith chapter 6.2 and also Goldsmith chapter 7. Okay, these are some very useful, the Q function approximation is in 6.2, this is where the Q alternative expression is, and then 7 talks about the diversity methods. Okay. So hopefully this is, this sort of completes the picture. We can do integration, we can do simulation, we can do numerical estimation, all of the ways in which, and all of them should give us the same result, and all of them give us very good insights into the topic that we are trying to study. If not, we move into another very interesting concept, the new concept for today's lecture. So the first question that I want you to think about, diversity, the following statement, is beneficial in fading. True? You would agree? Always? Yes? Under any condition is it not useful? Okay. Always true. Okay. Diversity in AWGN, is there a benefit? Okay, can't get better than AWGN, so why do you want to have? But let's see if that statement is correct. I agree with you. AWGN is the mildest of the forms of channel. So here is a AWGN scenario. R1 of t is S of t plus eta 1 of t. That's my first antenna. Second antenna also AWGN system, so is equal to S of t plus eta 2 of t. Supposing I were to add R1 of t plus R2 of t, what will I get? I'll get 2 times S of t plus eta 1 of t plus eta 2 of t. Maybe your mind is already thinking, well, you gained a factor of 2 for the signal, but you already added 2 noise terms. Maybe the net result is useless. Let's see what's the average SNR. average SNR, I must square the coefficient of the signal. So therefore, that gives me 4 times the whatever is the energy of the signal, Es. Total noise power is 2 times sigma n squared, 2 noise terms, that is equal to 2 times Es by sigma n squared. This is the SNR of a single antenna, So what did you get? You got a 3 dB benefit. So, well, why not take 3 dB? 3 dB is quite valuable in any channel. So there is a 3 dB benefit. Okay, so even in AWGN channels, there is some benefit for the diversity. Okay, now this benefit, which comes whether you have fading or not, is what we refer to as array gain. Why? Because I have an array of detectors. They add, all of them are picking up the signal. I'll explain in a minute. So let me just write it down. This is what is called array gain. Okay. Now, when you do averaging, supposing you have a signal that is very noisy, how do you remove the noise? You average it. Right? What do? You're adding several versions and then dividing by n. The scale factor does not matter. Now, what happens? What's the process that is happening? The signal is adding coherently. The noise is non-coherent. So therefore, the net benefit is that the noise variance goes down by a factor of m. So instead of, so you can think of this, you can interpret. Okay, let me just give you an interesting way to look at this. This expression, I can write it as Es divided by sigma n squared by 2, right? How will you interpret it? You will say same signal was transmitted, but it looks like the noise variance went down by a factor of 2. So if I have m antennas, what will be the expression? It will be Es divided by sigma n squared by m, as if your noise variance. This is exactly what averaging is. That's why averaging works. So the array gain is another way of saying averaging. The benefit of averaging is what you need. In diversity, if I just add the coefficients, yes, I don't get that benefit because the fading statistics did not change. But there is still an understanding of array gain, and that is very important for us. So the 2 types of gain that I want us to talk about, when we have multiple antennas are the following. The first one is I want to talk about array gain. In classical adaptive signal processing literature, this is also called beam forming gain. And historically, where does this come from? Beam forming gain. So if I have an array of detectors, and if I want to focus on an object that is coming from a particular direction, I must co-phase all of my received signals so that I get a beam in the direction of my desired signal. So my antennas are going to give me gain in a particular direction that is achieved through appropriate phasing, not co-phasing, appropriate phasing. So that is why it's called beam forming gain. Now, for us, we refer to it as array gain, and we will see in a minute how that these two are related. So array gain basically tells us that there will be an increase in average SNR. There will be an increase in average SNR even if there is no fading. Increase in average SNR because of the array benefit, even when there is no fading, even without fading, and that's what we saw in the case of the AWGN channel. Okay, and it occurs for all diversity techniques. Occurs for all diversity techniques. Diversity techniques. We are talking primarily about receiver diversity techniques here. So it can be selection combining or maximal ratio combining or equal gain combining, all of them will achieve it. However, the array gain is maximum for MRC. Maximum for MRC. Okay, the definition of array gain is G array, this is equal to average SNR under diversity conditions divided by average SNR of a single antenna. Okay, so this is average combined, that is combined under the diversity method. So let me just combined under whichever diversity method you are using, average combined or average diversity SNR divided by average single branch SNR. Single branch SNR. Okay, we already know what the average SNR is for the different diversity schemes. We already made the statement that average SNR of MRC is greater than or equal to equal gain combining greater than or equal to average SNR of selection combining. So therefore, this statement where that the maximum occurs for MRC is more or less something that is obvious to us, because for MRC this would be M times gamma divided by gamma, that is equal to M. So in other words, the maximum array gain possible is a factor of M, and that is achieved by MRC. Now comes the second one. Then what is diversity gain? Again, you told me now, we just now made a statement saying that there is gain even in the absence of fading. So what happens in the presence of fading? Okay, in the presence of fading, that's when we get the benefit of diversity gain. Now diversity gain is over and above array gain, over and above array gain, and this will manifest itself only when there is fading. If there is no fading, there is no need for diversity. Basically all you can get is the array gain, and this is primarily in fading environments. Okay. And what this is referring to is not the 3 dB or the gain that you get in the improvement in SNR. This gain is talking about changing the statistics of the gamma. Okay? There is a minimum benefit that you will get through the array gain, but what more can you get by changing the statistics? So basically this is focusing on a slightly different aspect. It says I'm combining the antenna signals with a specific intent to manipulate or improve or change the statistics of the distribution of the SNR. Antenna signals to get a more favorable PDF. Okay, maybe you understand exactly what we are referring to. More favorable PDF. Favorable PDF means I want to get a better BER for gamma. Okay? So in some sense, the more your PDF improves, mathematicians will be very angry when we write statements like this, but engineers are okay. If the PDF improves, the probability of error comes down. That's what we mean by in our case. This also means that the probability of outage will also come down if your PDF improves. That's what we mean. So this is where I believe once more the presentation of Say and Vishwanath comes in really handy in the way they have explained it. So you can look up the corresponding one in Say and Vishwanath. The basic definition same as what we have been using. So we will derive the or show the result that they have given. So the instantaneous SNR of the kth antenna is given by mod zk squared Es by N naught. Okay, that's the average SNR multiplied by the magnitude squared of the channel gain. Gamma MRC is equal to summation k equal to 1 through m gamma k. And this can be written as Es by N naught summation k equal to 1 through m mod zk squared. Okay, this is instantaneous SNR. This is instantaneous SNR. Instantaneous SNR. Average SNR can also be obtained for completeness, let's write that down also. Average SNR is expected value of gamma MRC. This is nothing but gamma times ES by N naught. I have written it as gamma. Expected value of summation k equal to 1 through m mod zk squared. Take the expectation inside. We know that if we have normalized our fading coefficients, then expected value of mod zk squared is equal to 1. So this will actually be equal to m times gamma. Okay. So now there's nothing new that we have written down. So what exactly did Say and Vishwanath, what is the insight that they give? So they said, okay, let's examine the instantaneous SNR. Instantaneous SNR. Said we already looked at it. What's there to look again? Let's look at it one more time. Instantaneous SNR. Instantaneous SNR is given by gamma MRC. I'm going to write it in a particular form that is very beneficial for us. M times ES by N naught. I'm going to multiply and divide by M, the expression for instantaneous SNR, and going to the remaining term is k equal to 1 through m mod zk squared divided by m is the second term. So basically this is I'm rewriting equation 1, instantaneous equation from 1. Okay, what we have done is just multiplied and divided by m. But notice that this is pointing us in the direction of m times ES by N naught is the same as m times gamma. So this is array gain. So the net gain that we get from maximal ratio combining, they have shown it as we can split it as two parts, one that comes from array gain and the other one that will come from diversity gain. Okay? Diversity gain. Now if I average the diversity gain, basically if I take the average, what will happen? 1. Because average of the numerator is 1, when you add up m of those, you will get m divided by m, it will become equal to 1. But where did you get the benefit? Because instantaneously, some of the ZKs may be bad, some of them may be better. Because you were able to combine them, you would have gotten a better statistics in the fading coefficient. That is where the benefit is coming from. So basically what we want to now compare is how does 1 over m summation k equal to 1 through m mod zk squared, how does that compare with mod z1 squared? Mod z1 squared, if you had only one term, if it goes into a fade, you are stuck. But when I have this type of an expression, then I am much more robust against fading. This is what is changing the statistics in terms of the statistics of the SNR. So as m increases, then what happens? We find that there is the probability of this being better than the diversity being better than the one without the case without diversity becomes more and more probable, because this is the one that is going to give us the advantage. Now very interesting for us to now is this part clear? So there is the array gain which will be there even when there is no fading. There is a component that seems to come in only when fading is present, and that too instantaneously it changes something. Instead of working with one antenna, it is trying to do a combination of antennas. And the argument is this combination is much more robust, because some ZKs may be down, some ZKs may be up. On average, I am up. That's the argument that is being made. Okay? So, but how do you visualize this? Back to our BER graph. The BER graph basically says this is BER versus SNR. AWGN graph is like this. Fading graph is this. If I had only array gain, what would be my graph look like? Two antennas, only array gain. it will be shifted by 3 dB, but it will follow the same graph, right. That is 3 dB benefit, this is array gain. 3 dB, that is 3 dB, and that is array gain. 2 antennas, but no benefit in terms of fading, I have not. But what is the graph that you get for 2 antennas, a maximal ratio combining? You find that the graph actually is this. So what is happening? There is of course array gain, 3 dB, and there is diversity gain. This is diversity gain. And the combination of these two is the net benefit that I receive, and this is why it is so important. So what this graph is showing is array plus diversity. This graph will be only array gain. Array gain will just be the same line shifted because it's only 3 dB or 6 dB, whatever is the number of antennas that you have, and this is the benefit that we achieve. Okay, so in layman's terms, array gain is a shift, a parallel shift of the BER graph. Array gain will contribute a parallel shift. Well, we will take the parallel shift, if that's all you get, but the important thing is to recognize that diversity gives you more than that. It's a parallel or a constant shift in the BER. The diversity gain, on the other hand, changes the slope. Diversity gain is a change of slope. Okay, and what we are seeing when we do things like MRC is a combination of array plus diversity, and the reason we want to separate it and not just call both of it diversity, just as one diversity gain term, is because there is a notion of how when we combine multiple sensors and you do beam forming, you get array gain. That's an SNR gain. So there is the notion that what comes from adaptive signal processing, which says, hey, there is an underlying array benefit, but over and above that, you have managed to change the statistics of the SNR, and therefore you get the so the change of slope is the important one. Now, which of them is more important? I won't argue. Take both. Both of them together gives us the benefit. So typically, what you will see when you are looking at the BER performance, you will find that the probability of error with respect to diversity typically will be of the form some constant 1 over average SNR raised to the power L. L may not even be an integer, but the slope will be some number, and typically L will be less than or equal to M. Less than or equal to M, where M is the number of antennas. M is equal to number of antennas. Okay. If you manage to show that L is equal to M, you have achieved full diversity. Okay, that's the best that you can achieve. But so L is called the diversity order of the system. L is the diversity order of the system. That's the slope of the graph. Diversity order of the system. And if you have a weak antenna or if you have a correlated antenna, then you will not be able to achieve full diversity order, but it will be less. So typically, L equal to M implies you have achieved full diversity for your full diversity benefit and full diversity performance gain for your system. Typically, if L is less than M, that's probably due to either you have some weak antennas or you have some correlated antennas or some whatever reason you have not been, or you didn't implement, you were a little lazy and you didn't want to do MRC, you did EGC, you didn't get the full benefit. Okay, that's because of the choice that you have made. But at the end of the day, the slope is what matters. You have either correlated antennas or due to implementation losses, whatever may be the cause for this. Implementation loss, your channel estimation was not good, whatever it is, you achieved something that is less than M, but that's your diversity order of the system. Okay? that gives us a complete picture of what we need in terms of the understanding of diversity. Any questions? Now comes the acid test. Okay, now this is a crucial question. Let's say that this was going to determine the grade for the course. Okay, the question is, I have the following situation. Fading environment. Antenna 1 antenna 2 okay, 2 students. Student A says it's a waste, throw away one of the antennas, no benefit. It's fading environment, correlated antennas, I know no use, right? Throw it away. Okay, even under this environment, array gain will still be there. So don't throw away the second antenna, you will still get 3 dB antenna gain, array gain. Whenever the original signal faded, this will still fade, but you would have boosted your average SNR by 3 dB. So that's very important. So, so in this case, diversity gain nil. You did not change the slope of the diversity, but you still got array gain. Now, if it so happened that the 2 antennas were not so identically correlated, then you would start to get some diversity order, and then if they are totally uncorrelated, you will get full diversity order. Okay, good. I'm very happy with that. So this would be a case where if you actually implemented it, you will get BER slope equal to 1. You will get, if you took the array gain, you will get the benefit. You will see a graph which has got the same slope but 3 dB better. Okay, so this is why, and you've passed with full marks. Okay. Now, one last piece of information, or probably some notation that's very important for us. So, transmit diversity. We already gave an example, but let me just introduce some notation for us before we go into one of the most interesting case studies in transmit diversity. Transmit diversity basically says that I have a transmitter which has got multiple antennas. Let me just show the case of 2 antennas, and I have one antenna at the receiver. So this is my transmitter, this is my receiver. Of course, it need not be limited to 2, I can have anything more than 2 as well. The channels are uncorrelated, Z1, Z2. We know that we have to split the power, so 1 by root 2 has to be applied to each of these terms. Now, we will do this block, we will call it as diversity pre-processing. Pre-processing, which means that you have to do something to the diversity signals before transmitting so that you get the benefit. So what exactly, what was the thing that we said, that we will not transmit just S of t from each of these branches, we will transmit Z1 star divided by root 2 times S of t from this branch, we will transmit Z2 star by root 2 times S of t from the second branch, and that's when we will see co-phasing of the signals at the receiver. Now, for this, we needed this block on the right hand side to do the following. It needed to estimate Z1 and Z2, okay, and it also had to feed back this information, and that was the feedback channel. So this was, it's feeding back Z1 comma Z2. Now, this framework has got some notation that is very, very useful for us to remember. Now, Z1 and Z2 are referred to as channel state information. Channel state information. The channel conditions are described by Z1 and Z2. Channel state information, which is popularly denoted with the acronym CSI, channel state information. Now, the minute the receiver is estimating CSI, we refer to the information here as CSIR. because what is the true channel is CSI, what I estimate at the receiver is CSIR, okay, and so far the transmitter does not know what is happening, but if I do feed this information to the transmitter, then I say that channel state information is also available at the transmitter. So CSI in the channel, CSIR in the receiver, if I feed it back, it is this information that is sitting at the transmitter is now referred to as channel state information in the transmitter. Okay, that's notation, but it is useful for us to keep that picture in mind. Now I want you to think about a transmit diversity scheme, which was, it's a very powerful scheme. So transmitter 1, transmitter 2, this is receiver, channel Z1, Z2. Now Alamouti is the name of a person, 1998. He proposed the following. He said, I am going to transmit two different signals, x1 of t from antenna 1, x2 of t from antenna 2, and I am going to receive them at the receiver. If he had put x1 of t and x1 of t, what would you have told him? Don't do that, it's a waste of time, because there is no benefit from doing that, because we already know that. You might, if you are smart, you would do co-phasing by pre-rotation. He says, no, I am not interested to know the channel. Let us say, wait a minute, you don't want information at the transmitter, then I think you are in trouble, because I don't think you are going to get any benefit out of it, because unless you know Z1 and Z2, there is really not, we are not sure or you can get any benefit. So this is what Alamouti said. He said R of t is going to be Z1 times x1 of t plus Z2 times x2 of t plus eta of t. Okay? Now Z1 and Z2, I have written them as if they are constants, but these are actually time varying Rayleigh coefficients. Okay? One particular snapshot is what we have shown. So therefore, these are Rayleigh time varying random variables with Rayleigh statistics. Okay, so that's something that you keep in mind. Okay, now x1 and x2 are two different signals. So if I transmit both of them at the same time, they will interfere with each other. So x1 of t and x2 of t are now interfering with each other, and x2 of t are interfering. Okay. Now, what is the C over I? C over I, carrier to interference ratio. Forget the noise. X2 are of the same level, 0 dB. So C over I is approximately 0 dB. So which means that no detection is going to be possible. I have to ask Alamouti, are you sure you know what you are doing? So this is what he says he wants us to do. So this is time, this is antenna 1, this is what he is going to define as x1 of t, this is x1 of t, x2 of t, which is antenna 2, and he said this is time, n equal to 1, n equal to 2. And he says antenna 1 you transmit S1 and S2, whatever you are going to transmit normally, symbol number 1, symbol number 2. But antenna 2, he says you transmit minus S2 conjugate and S1 conjugate. Okay? And then we say, well, okay, I don't mind, you asked me to do this, let me. So he says write down the equations. So at n equal to 1, R1 equal to Z1 S1 minus Z2 S2 conjugate plus eta 1 of t. Correct? What was transmitted by antenna 1 at time 1, what was transmitted by antenna 2 at time 1, multiplied by the corresponding coefficients and then added together. Then at time n equal to 2, R2 equal to Z1 S1, Z1 S2, Z1 S2 plus Z2 S1 conjugate plus eta 2 of t. Okay? So now the statement that was being made is obviously these are, now I have two equations and two unknowns. So, maybe there is some hope for us what we are doing. So, he said do Z1 star times R1 plus Z2 times R2 conjugate. You can easily verify and do that, and you will find that what you get is mod Z1 squared plus mod Z2 squared times S1. What is that? That is like maximal ratio combining, okay, times S1 plus noise terms Z1 star eta 1 plus Z2 star eta 2. Okay. So, basically there are some couple of noise terms that are present, and likewise you can write a combination that gives you S2 also with the diversity expression in front. Okay. So, what is Alamouti actually doing? This is the first transmit diversity or the space-time code where you transmitted different signals but managed to get the benefit of diversity and interference cancellation, because only if you cancel the interference you can detect the signal. You cancel the interference and you got the benefit of diversity. That's space-time coding, and this was the first illustration of space-time coding that was demonstrated, which then of course opened up the entire field. But how did Alamouti work on it? What is the array gain that he achieves? Is there a diversity gain? Let's answer those questions in tomorrow's class. Thank you.